So today we're going to be taking a look at describing two different types of bonds, metallic and ionic. They have some similarities in how the structures of the atoms are involved, and you should be able to connect some of the properties of these types of bonds to the properties we see in the elements and compounds that have them. With a metallic bond, what's happening is that the valence electrons of atoms in a pure metal can be modeled as a sea of electrons. We mentioned that metals tend to have fewer valence electrons than half in that outer shell, and they have a tendency to give them up. There's very little ionization energy needed. That's one of the reasons that we see metals tend to be able to conduct electricity. There are these electrons that are able to be free floating and move amongst the ions that are formed when those electrons are given up. A metallic bond occurs when we have these force of attraction occur between the free-floating valence electrons and the positively charged metal ions around them. So if we take a look at this animation, we see that the E negatives floating around the Mg plus ions here represent a crystalline structure, making that kind of regular three-dimensional shape with the electrons moving in and amongst these positively charged ions. It's like a flowing of water amongst these different structures within it. So when it says it's a sea of delocalized electrons, those electrons have been given up and can move freely. This is what accounts for, like I said, some of those properties like malleability and conductivity. We'll see some similarities in the way that these structures are created, the crystalline structures, much like some of our ionic compounds. Now, as we move into ionic bonds and ionic compounds, these are things that by definition will have two or more different kinds of elements that make them up. The bond will occur when two or more atoms of these different elements form an attraction together. One of the things we need to be able to do is account for the electrical charge in an ionic compound and talk about properties that are typical for these types of compounds. We have seen some introductions from the How Does Charge Matter demo. We've already mentioned before in some of our activities that a cation and an anion is required when I form an ionic compound. Even though we have charged particles within them, the charges cancel out, so they are electrically neutral. Our overall charge is zero. Because you have opposing charges, it is those attractions to each other that hold the ions together. This typically will form when there is a difference in electronegativity of about 1.7 or more. So if you recall from last unit in our periodic trends, the far right side of the periodic table, or our nonmetals, when they bond with many of our metals on the far left, meet that criteria. In this situation below, between a sodium and a chloride atom, what we see is that there's such a great pull from the chlorine, it doesn't just hold on to them more, it actually rips that electron off and takes it for itself because it has such a great attraction for the electron in the bond. Once these two create that force of attraction bond, what's happening is the electron has actually been transferred from the sodium to the chloride ion. And then your attraction occurs between the positive sodium and the negative chlorine ion. So the biggest part here is this transfer of electrons. For an ionic bond to form, electrons transfer because of the great difference in electronegativity between the positive ion and the negative ion elements. So an ionic bond will form when one or more electrons is transferred from what will become a cation to an anion, so that both ions have formed. So both ions formed have a charge and attraction to one another. Now the cation is typically going to be a metal, and the anion is typically going to form from a nonmetal in many cases. But the more concrete part that must be true is the cation and the anion. So again, sodium would have that single valence electron to give up. The chlorine would pull it off because of that strong attraction to fill its outer shell to then create NaCl as the compound. Now the chemical formulas for these are going to show the number of atoms of each element and how many. These are things we've seen before. We know that water is H2O. We've already seen some examples and worked with some naming in our POGL. You've also, you will have some practice today at writing out some of those naming rules based on these examples that we've seen. Now the formula unit is the correct way to represent that smallest ratio of ions in an ionic compound. When we talked about our charge demo and our conductivity, we showed that they tend to exist in crystalline structures. You don't have these individual units of, say, one Na and Cl bonded together. It's you have an alternating pattern in a three-dimensional shape. But there's always a lowest ratio of the ions in the compound. Now we've looked at something like sodium chloride. There was one electron given up by the sodium, and the chloride ion only needed one more to form. Now in the case of something forming between a magnesium and a chlorine ion, notice that magnesium has two electrons to give up. Since chlorine only has one space to fill, we would need two chlorine atoms to be able to transfer all of the electrons that magnesium has to give up. So Mg, being a 2+ ion, would need two single chlorine ions to be able to have 0 overall charge. So that's why we would have MgCl2 as our compound. Now when we draw that out with the dots like this and show our bracketed dot models next to each other, we call that a Lewis structure. The Lewis structure is going to represent those valence electrons for all atoms within the compound. For something like an ionic compound, we're simply showing that lowest ratio in an alternating pattern. I've color-coded the electrons to show who started with what and what was transferred. You don't have to do that when you do your own Lewis structures. Now, a couple examples. Sometimes people find it easier to show this with a visual. So when we are looking for it, one way I like to do it is to draw out the actual charges. Magnesium, we said, makes a +2 charge, so I've drawn two positive signs, and chlorine is a -1. What I then do is simply circle each pair, and as long as every positive is matched with a negative, I'm good to go. Well, in this case, I still have that positive charge hanging out, so I need to bring in another chlorine atom. When I do that, I am then able to make another pairing of the positive and negative, and I have no charges left over, giving us our MgCl2. Wrong one. There we go. Now when I look at something like an iron 3+, combining with a sulfide ion, here I have a +3 and a -2. Hopefully we can see that we're not going to be able to pair up easily from the start. I'm going to need more sulfide ions. Right now, I have one positive charge left over. So let's grab another sulfur. Once I go here, I still have a negative left over, so that's why we're going to need a second ion of iron. Notice though I had to bring all of the positive charges along for the ride. I can't just put on one more to finish it out. So I'm going to make a pair here, and I need another sulfide ion now. Once I get that third sulfide, I should be able to pair up everything evenly. Every positive cancels out a negative, and that's going to give me Fe2S3. Now what I did here is I have a total charge of +6. And my negative charge is a -6. And when that is true, when my positive value is equal to my negative value, I'm going to have an overall charge of 0. So I have 2 times +3 gives me my +6. 3 times -2 gives me my -6 to cancel it out. The other rule example I gave us was the crisscross method. So we said in class that if I take the cation's charge and make it the subscript of my anion and do the same across, I will automatically cancel out my charges because I'm going to be multiplying by the other number. So here, that also gets us our same one from before of Fe2 S3. The only time we have to pay attention to that, be a little bit careful. If I have something that's in multiples, remember we always have to have our lowest ratio. Here, I would have PB 2O4, but that's actually going to be equal to PB O2. I have to reduce it to its lowest ratio. As long as you make sure to reduce after crisscrossing, you should be good to go. Now the last piece we're going to take a look at are those properties. We saw some of them, that they're solids, they're crystalline. We saw that kind of shiny material and those small particles when I brought them around the room in the demo. Because of that strong attraction between the positive and negative, it takes a lot of energy to get it to change phase. So they have really high melting points. But because they are formed by ions, when they do melt and separate into those ions, they are able to conduct a current. We can also get this to occur by dissolving in water. That polar water molecule is able to get the ions to pull apart, and that is able to allow that current to be conducted as well. This concludes the notes that you need to take that will help you to be able to work on the naming in the next step. Make sure that you have completed the notes that are required through the front page of the packet.